about the scaling limit for heavy tail ballistic deposition with p-stick.
Okay, thanks, Ines, for the presentation. It's a pleasure being here. So today I'm going to be talking about some joint work with Francis Comets and Joseba Dalmau, which has some time already. But okay, I think it's nice, so it's worth giving the talk here again. So this is supposed to be like a simulation of ballistic deposition, but somehow it's not working. But don't worry, I'll show you pictures afterwards. So okay, so we worked with Francis and Joseba. We worked with a slight modification of the standard ballistic deposition model. But before I can tell you what we did, I think it's best to start with the standard ballistic deposition model, which I guess most of you are familiar with, but maybe some of you are not. So I'll start with that. So the standard ballistic deposition model, and I'm going to be looking at the model with a sticking parameter P. I'll explain what that is in a second. Is a model for surface growth, for the growth of a surface or the evolution of an interface, which somehow separates two different phases of a system, can be kind of modeled by a growing surface somehow. And in this model of ballistic deposition, our surface is going to be modeled by a cluster of blocks like the one you see here. This is going to be my surface, okay? And the way the surface is going to grow is that, like at rate 1, unit blocks are going to get attached to it. Okay, they're going to like fall down from the sky, and they're going to get attached to it, making the surface bigger and bigger. Okay, so to be more precise, this cluster of blocks is going to evolve, or is going to grow as follows. Okay. So I'm going to have the real line, and above each integer site x, like this one, for example, I'm going to have 1 by 1 blocks, like the ones you see here, falling vertically down at random with rate 1. So that means that for each site x, I have a Poisson process, which is independent for the different values of x, such that, okay, this Poisson process has rate 1, and each time the Poisson process rings, a block falls down on top of x, okay? But the thing is that, okay, once a block like the green one here is trying to fall down on top of x, two things can happen, okay? So the block will somehow flip a coin. The coin will be heads with probability P, or tails with probability 1 minus P, sorry. And all blocks will have like independent coins. And if the coin is heads, so that with probability P, the block will choose to stick to the first point of contact to the surface, will choose to stick to the surface at the first point of contact. So in this case, that would be this corner right here. Okay, I will show you a picture afterwards, but okay. And with probability 1 minus P, so if the coin is tails, it will just disregard the first point of contact and will go straight down on top of the last block sitting above X. Okay, so I'll show you a picture. It will be more clear. Okay. Again, the simulations are not working, but okay, never mind. So this is the situation. This is kind of the current cluster of blocks, my current surface, and some new block is trying to fall down on top of X. And it's gonna draw or flip a coin, and with probability P, it's gonna choose to stick to this corner right here, and with probability 1 minus P, it's just going to go straight down and sit on top of this block right here. Okay, so for those of you who are more familiar with ballistic deposition, like the real original ballistic deposition model is a bit different, because when a block decides to stick to the first point of contact, that's actually kind of the side of this neighboring block. Okay. But for reasons which will be apparent in the, I guess, next 2 slides or something, For us, it's going to be more convenient to stick to the corners, okay? So that's kind of one difference with the true original ballistic deposition model, but it's not such an important difference, so I guess it's fine anyway. And okay, so I brought animations of two different models corresponding to two different values of P. So if P is equal 1, we get what we call the standard ballistic deposition model. And that means that each time a block tries to fall down on top of some site X, it will stick to the first point of contact always, okay? That's P equals 1. And P equals 0 is a different model called random deposition, in which the blocks don't look at nearby columns, they just fall straight down and disregard completely the first point of contact. They just fall down on top of X and sit on top of the last block, which was deposited before it. And so, okay, so in this case, okay, let me go back. Basically, the columns behave independently because the blocks just fall straight down. And in this case, there's dependence between the evolution of different columns, okay, of blocks. Okay, so this block right here, whenever it decides to stick to the first point of contact, is going to have to look to the sides to see where that first point of contact will be. Okay, it can be either in this column or this one in this case, or the one to the right. Okay, so there will be some dependence between the columns. And this dependence will exist as soon as P is positive. Okay, if P is equal to 0, there's no dependence, but if P is positive, then the evolution of each column will depend on the neighboring ones. Okay, so is the model clear? Do you have any questions at this point? Let me turn to the chat. No. Okay, I guess that's fine. Okay, yeah, no, these things are not working. I'm sorry. Okay, I'll show you some pictures afterwards. But okay, so what do we know about this model? I'm still not talking about the actual model that we worked with Francis and Joseba, but what do we know about the original model? So if we fix some site in the integers, let's say X, but it can be to fix ideas, it can be the origin, and some time t, and we define h of xt as the height at time t of the column of blocks sitting on top of X, okay? And that means, so let me go back. So for example, here, the height above X will be 1, 2, 3, 4, okay? Because the last block is at height 4, okay? Okay, so if we define h of xt like that, then for p equals 0, which is the random deposition model, it's called random deposition. Okay, each of the columns behaves independently, and what you actually get is a Poisson process. Okay, at rate 1, the height of the column just increases by 1 each time a block gets deposited on top of the column. So in particular, the height will grow linearly with time, and it will have Gaussian fluctuations, okay, because it's just a Poisson process. Whereas for p equals 1, which is the standard ballistic deposition model, what we know is that the height also grows linearly with time. The constant might change, but okay, it still grows linearly with time. But now the fluctuations should not be Gaussian. It's conjectured that the fluctuations should be in the KPZ universality class. So this is a model which is supposed to be, it's conjectured to be in the KPZ universality class. So in particular, the fluctuations should be of order 1/3 instead of 1/2. Okay, t to the 1/3 instead of t to the 1/2, which is the case of this Gaussian fluctuations. Okay. Okay. So great, but this is only a conjecture. So we know that the height grows linearly, but the fluctuations are believed to be in this KPZ universality class, but there's no proof. And okay, it's kind of difficult to give a proof because this is an example of a model which is not exactly solvable. Okay, so there's not much that can be done in this setting. Okay. So the question that somehow drove us to study, well, a variant of this model is the following. So how does the system transition from one type of behavior for p equals 1 to the other type of behavior, Gaussian fluctuations, for p equals 0? Okay, so how does the system transition as one goes from p equals 1 to p equals 0? Okay, is there a kind of a phase critical parameter of p? Is there a level? Okay, what kind of phase transition is happening? Well, we know that for p equals 0, the behavior is different for p equals 1, but okay, we want to understand somehow what's the transition like. And okay, the answer, or to give us some kind of answer to this question, is too hard for us at the moment because we're actually not even sure what's happening at p equals 1. We think ballistic deposition should be in the KPZ universality class, but we don't even know. So to try and say something when p goes from 1 to 0 is even, I guess, harder. So this problem is too hard for us at the moment. So the idea that Francis had actually is to try and ask the same kind of question in a different model where we can try and study this transition, okay? And so this is where the heavy tail ballistic deposition model comes in, okay? So the heavy tail ballistic deposition model, which I will explain in the next slide, suffers like a similar transition, not at the level of fluctuations, but at the level of speed of growth of the height. And this transition is the one that we're going to study, okay? Okay. Okay, any questions maybe while I regroup? No, okay. Okay, great. Okay, so this is the model that we're actually going to be looking at. So the heavy tail ballistic deposition model with p sticking as before is the same as the one I explained before as ballistic deposition, with the only difference that the blocks which are falling down now will have random heights. They will have width 1, but their heights will be random. And there will be i.i.d. for the different blocks, okay, with some common cumulative distribution function f, which we're going to assume satisfies the following two hypotheses, okay? First, this distribution function is going to be 0, 0. So that means that all blocks will have a positive height, basically, a strictly positive height. And moreover, the height of the blocks are going to be heavy-tailed, okay? So the distribution function f is going to have a right tail, which is going to be regularly varying, with some index alpha in between 0 and 2, okay? So that means that the tail of the distribution is going to behave like t to the minus alpha, for some alpha in between 0 and 2, times some correction, okay, some LT, which is going to be a slowly varying function. So for those of you who don't know what that is, okay, that's kind of a function which decays slower than any polynomial. So grows or decays slower than any polynomial. So maybe a logarithm or something like that. Okay, that's kind of the idea to keep in mind. And okay, so you can see here, okay, that's kind of an old picture of what the model looks like. Then in this case, we have blocks which are super tall, right? Like this one, for example, okay? And that these particularly tall blocks somehow seem to have like a deep impact on the growth of the surface, okay? So this doesn't look anything like the original ballistic deposition model, which all blocks somehow had the same height. And so we couldn't see this because the simulations were not working before, but actually I'll show you some pictures of the standard ballistic deposition model, and you'll see that, okay, the picture is quite different from this. And okay, so for this model, what we're going to see is that depending on the value of p, the rate of growth of the surface is going to change in principle. And so what we want to do is that we want to understand how this rate of growth depends on P, okay, as T goes to infinity. Okay, great. Okay, so I'll show you the pictures now, okay. So these are our simulations, okay. So what we did basically, maybe let me zoom in a little bit. So what we did is we took like a finite, like 400 integers basically from 0 to 400, and we deposited 1,000 blocks essentially, okay. So the colors that you can see here somehow represent the age of the blocks. The blue ones are the ones that got deposited first. The green ones are the ones that got deposited last. And okay, and this is the heavy-tailed case. I think that we used the Pareto distribution with some alpha, maybe 1.5. I don't remember right now. But if you compare it with standard ballistic deposition, okay, the picture is actually quite different, right? Because here, kind of the growth of the surface seems to be somehow governed by this huge blocks that we see right here, okay, which kind of thrust the surface up somehow, okay. Whereas here, everything seems to be, I don't know, okay, much more homogeneous in some sense. Okay. So that's kind of the comparison between the two models. This is for P equals 1, okay? And this is kind of a comparison for heavy tail ballistic deposition, in the case P equals 1 and P equals 0. So the model of random deposition, where all the columns are independent. And here you can see that, again, the behavior is quite different. So here, okay, the kind of the blocks can look at the neighboring columns when deciding to stick to the surface, and here all the columns behave independently. So the kind of surface that you get seems to be quite different. Okay. Okay, so those are kind of the pictures to convince you somehow that this heavy-tailed ballistic deposition model that we're looking at is very different from standard ballistic deposition with unit block heights. So it's not in the KPC universality class. And this ballistic deposition, this heavy tail ballistic deposition model is also very different for P equals 1 and P equals 0. Okay. Okay. So what did we show with Francis and Joseba? So our first main result is the following. So if we denote by h of xt semicolon p, the height above the site x of the cluster or the column of blocks sitting on top of x at time t, for the model with p sticking, okay, so where each block flips a coin with which is heads with probability p or 1 minus p otherwise. If we denote the height like this, and we assume that we start with a flat initial condition, so at time 0 there are no blocks sitting on top of the real line, okay, then what we were able to show is that there exists a slowly varying function L sub f, which is related to the distribution of the block heights, but it's not the same slowly varying function as before. Okay, it's related to that one. So let me go back. It's not the same as this one. It's related to that one, but it's not the same. Okay. In such a way that if you fix any sticking parameter P positive, okay, and you fix any site, then as T goes to infinity, when you scale the height by this, okay, the normalized height converges in distribution to a limiting object, which first of all doesn't depend on P. Okay, so basically what this theorem is telling you is that the dependence on P somehow gets washed away in the scaling. Okay, that's kind of the only influence of P in the behavior of the height. Okay. And second of all, okay, this limit h we can like fully characterize in terms of a specific variational formula that I will tell you about in a couple of slides. Okay. So this is our first result, which, okay, basically tells you the asymptotic order of magnitude of the height as t goes to infinity. And okay, that basically there's a random constant accompanying or going along this order of magnitude, okay? Okay, so I want to recall that, so alpha is in between 0 and 2, okay? So in particular, if you, okay, disregard this, which is kind of a slowly varying term, you can think it's like a log, so it doesn't really matter that much, a little bit, but not that much. This right here, for p fixed, behaves like t to the 2 over alpha, okay? And this is much larger than t, okay, because alpha is less than 2. So in particular, what this is telling you is that the fact that you have heavy-tailed heights makes the surface grow faster than linear, okay? So it's completely different from the ballistic deposition, the original ballistic deposition model, okay? Here you have like a faster growth. Okay. And so that's for p positive. What happens for p equals 0? For p equals 0, the behavior of the model is different because, okay, as I said, all the columns behave independently. And okay, at rate 1, what happens for each column is that at rate 1, a block is going to fall down on top of the last block sitting on top of x. And this block will have a random height, which is going to be distributed according to this distribution function f, okay? So basically, if you look at each column separately, then the height above the height of the column is going to behave like a compound Poisson process with this jump distribution f, okay? And so by the generalized central limit theorem for heavy-tailed distributions, this is going to happen, basically. So if you take h and you center it by some constant c of t, which I don't want to explain what that is, doesn't really matter, it depends on alpha. And then you normalize by t times a slowly varying correction, then this will converge in distribution to some stable law of index alpha, okay? In particular, I didn't tell you what c is, but this, okay, trust me, believe me, this tells you that for p equals 0, the height for of the column of blocks sitting on top of x is going to be much smaller than the height in theorem A. Okay, so in the case where p is positive. Okay, so when p is positive and you can look at neighboring columns, this somehow helps the surface grow faster. Okay, than in the case where you just have like depositions, random depositions on top of each column, and you don't look at the sides. Okay. So what we see here is that, okay, the speed of growth depends on p. For p positive, essentially the speed of growth is the same. It's like a constant depending on p times t to the 2 over alpha, okay? Times h if you want, okay? And for p equals 0, it's less than that, okay? It's a slower speed of growth. So we kind of have the same phenomenon as before. The system behaves in one way for p positive, and for a different way for p equals 0. And so now we can ask the same question. What can we say about the phase transition as p goes from 1 to 0? Okay. And okay, so this is our next theorem, which says the following. Okay, so okay, so let me say something before I get to theorem B. So if you want to think of a phase transition somehow, what this theorem A is telling you is that the critical parameter of P is 0, actually, okay? Because for positive, you have one kind of behavior, and for P equals 0, you have a different one, okay? So if you want to understand what that transition looks like in more detail, what makes sense is to somehow let P go to 0 with t, okay? And this is exactly what we did for theorem B, okay? So theorem B says that, okay, if you fix some gamma in between 0 and 1, And for each t, okay, you're going to take now the sticking parameter of a form t to the minus gamma. Okay, so when t goes to infinity, the sticking parameter will go to 0 polynomially somehow. Then the system, which is basically, okay, you can think that x is 0, so the height at time t above the origin, okay, of the column of blocks above the origin, for the model with sticking parameter pt, okay, t to the minus gamma. So that means that if I change t, okay, I change the model because now the sticking parameter depends on p. Sorry, depends on t, okay? So what I'm doing here when I'm looking at this collection of random variables is that for each value of t, I'm looking at actually a different model, okay? But okay, so for each value of t, I look at a different model. I look at all these random variables together, and it turns out that this collection exhibits a phase transition at this critical parameter of gamma, which is the minimum between 1 and 2 minus alpha, okay? Where alpha is this kind of the decay rate of the tail of the block heights, okay? Of the block heights distribution. So what happens is the following. So for gamma less than gamma c, so that means p going to 0, but not too fast, okay? Then what you see is the same thing as in theorem A, okay? So the system somehow still behaves in the same way as it did for a fixed value of p larger than 0. Okay, so if you, seems somehow natural, if you make p go to 0 but not too fast, then the behavior of the system is not going to change too much. Okay, whereas, okay, fine. Whereas for gamma larger than 1, okay, what we're going to see is that the system, okay, behaves like the system without any sticking. Okay, like the system for p equals 0. So as soon as pt is much smaller than 1 over t, basically what you see is this random deposition model. Okay, it's like the columns were independent somehow. Okay, and okay, what happens in between? Okay, so for gamma, in between this gamma critical and 1, which I should say that this only happens if alpha is in between 1 and 2, okay? So if alpha is in between 0 and 1, okay, then gamma critical is just 1, okay, because this thing is going to be larger than 1. So basically, if if alpha is in between 0 and 1, then these two things are the only things that you're going to see, okay? So you have like the ballistic deposition or heavy tail ballistic deposition, and then suddenly you just become random deposition. Whereas if alpha is in between 1 and 2, then on this intermediate window, okay, we actually don't know exactly what's happening. We don't know if we have like random deposition or what exactly is going on. But what we do know is that the height of the column of blocks grows faster, okay, than in the case of a fixed value of p, okay? So that then in this case, okay? So somehow what this is telling you is that on this intermediate window of gammas, the system behaves differently. It doesn't behave like the case for a fixed value of p, okay? We still don't know if it behaves like random deposition or if it behaves like something else, but it doesn't behave like this, okay? It grows faster. Okay, so those are the two main results. I don't know if you have any questions. Maybe that will be a good time to ask questions. No. Okay.
I actually have a quick question.
Yes.
About the model. Are you changing as it evolves? Do you change the P, or is it that you look at the problem at a time depending on P that you chose?
So I'm changing the model as I change T. I'm not looking at a single model where as T evolves, somehow the sticking parameter evolves. I'm fixing a T, okay, that gives me the sticking parameter, which is going to be t to the minus gamma. And then I construct the ballistic deposition model for all times, if you want, with sticking parameter t to the minus gamma, okay? And then I look at that model at time t.
So to put it differently, you choose a P and then you choose the moment of time depending on P to look at. That's the moment of time you're looking at.
Yes, essentially, yes.
Thank you, that
want.
clarified my issue.
Okay.
A question.
Yes.
In the third case, you are going to infinity. So maybe if you normalize it differently, may have a limit, right? So have any clue for?
Yes. Okay. So maybe, but we don't know. So what I can tell you is that this grows at least as fast as random deposition. So random deposition grows like, well, like this, essentially, depends on the constant here. So in that case, it will grow at least as fast as random deposition, okay? But we don't know if it grows in at the same speed or not. We don't know exactly what's happening, okay? But yeah, maybe, yeah, we don't know what's the correct order of magnitude of this height, okay, in this case. Okay, okay, so let me, well, before I get to the proof, let me try to explain what this limit h is, okay? Yeah, so, and then explain a little bit about the proof. Okay, so to explain what this limit h is going to be, I need to define a few things. So first I will define a set of paths, okay, which I'm going to call L. So it's going to be the set of paths from the interval 0, 1, taking real values, okay, which somehow end at 0. So S of 1 is going to be 0. And they need to be 1 Lipschitz. So that means that they need to be Lipschitz with constant less or equal than 1, okay? So that's going to be my space of paths, okay? Which is going to appear in this variational formula, which defines H. And then I'm going to define a set, which I'm going to call like triangle or cone, if you want, which is essentially this triangle right here. Is the triangle of vertices 0, -1, 0, 1, and 1, 0. And what this triangle or this cone, well, let's call it triangle for now, but later it will be a cone. What this triangle represents somehow is the space where the graphs of all paths here actually live, okay? So if you take a path here and you draw its graph, okay, then because it needs to end at this vertex right here, and it needs to be 1 Lipschitz, then essentially its graph needs to be contained in the triangle, okay, but essentially all paths which are in L will have a graph which is contained in this triangle, and this triangle is somehow the minimum set which contains all the graphs of these paths, okay? Okay, great. So that's one thing. And now what I'm going to do with this triangle is I'm going to allocate points inside the triangle, okay? And each of these points is going to carry an independent weight, okay? So first I'm going to say how I'm going to allocate the points. So I'm going to consider a sequence UN of i.i.d. random variables, which are just going to be uniformly distributed on the triangle. So the locations of the points are going to be uniformly at random, okay, and independent. And then I'm going to assign to each of these locations a weight, which is going to be chosen in the following way. So I'm going to consider a sequence of i.i.d. exponential random variables of parameter 1, xn, independent of the UNs, okay? And I'm going to define a random variable, or the random variable mn, by this formula right here. So it's 1 over the sum of the first n random variables xn to the power of 1 over alpha, okay? And so this is going to be the weight which somehow accompanies or comes with the point sitting at the position un, okay? So we're going to think of mn as a positive weight located or positioned at the position un inside the triangle, okay? And once you have these two things, okay, you have the positions and you have the weight assigned to each position, then we define our limit h as the maximum sum of weights that can be collected by any one Lipschitz path, so by any path in L, okay, which ends at 0, okay? So essentially, you look at all the paths in L, and you see how many points or so how many weights they can collect, and the maximum sum of weights that they can collect, that's the value of h, okay? So for those of you who are familiar, this is actually like a last passage percolation problem, which is not on a lattice, but actually on a continuous triangle somehow. So the points are now distributed uniformly on the triangle, and we have something which looks like a last passage percolation problem, okay, in which the paths are not just increasing paths like they usually are, but they are like one Lipschitz in this case, okay? Okay, so that's the definition of H. And so the question is, how much time do I have? Maybe 15 minutes, 10? Okay, I'll continue talking and then you'll tell me. I don't know. You don't need to run. Okay. So the question is, what's the relationship between...
Yeah, you have 10 minutes or 20 minutes. You started in 2 minutes past the hour.
So how much?
Meramente, so? 20.
20?
Yeah.
Okay.
Let's say...
We'll start doing like this and I stop. Okay. So the question is, okay, what's the relationship between ballistic deposition and last passage percolation? I mean, because they're completely different models in principle. And so why I'm getting a last passage percolation problem as the limit of ballistic deposition, okay? And so to explain what's the relationship between the two models, I will just focus on the case with p equals 1, okay, for simplicity. But for any p positive, this is the same kind of idea, okay? And to explain what's the relationship, I need to go back to somehow the graphical construction of the ballistic deposition model, okay? So to construct the ballistic deposition model, heavy-tailed ballistic deposition model, what I need basically is to know the different times when the blocks fell, okay, and stuck to the cluster of blocks. And what I need to know is, okay, at what time did they fall, on which side did they fall, and what's the height of the block. If I have all that information, then basically I should be able to reconstruct the process, okay? And the question is, how do we reconstruct the process from all that information, okay? So I'm going to explain that now. So to do this construction from that information, I'm going to encode this information, kind of the positions of the blocks, the times at which they fell down from the sky, and their heights. I'm going to encode all this information with a sequence of Poisson processes, okay? So for each, this is going to be kind of the integers, and for each integer, I'm going to have a Poisson process, okay, with rate 1, which is going to be independent for the different values of x, for the different integers. And okay, each of these red crosses is going to represent an occurrence or a point in the corresponding Poisson process. And for example, that you have here a mark or an x at 0 at this particular time, okay? What it means is that at that particular time, a block tried to fall down on top of 0, okay? So basically that the red cross is t, x means that the block fell down above side x and stuck to the cluster of blocks precisely at time t. Okay, so this is telling me when and where the blocks fell. Okay, and so the remaining information that I need is the height of the blocks in order to compute or in order to construct the process. And so what I'm going to do is I'm going to attach or assign to each of these crosses in the Poisson processes. I'm going to assign a mark. Okay, so each of these red crosses will come with a mark, okay, which is going to be independent for the different crosses, and this mark will be exactly the block height, okay, which will represent the height of the block which is falling down at that time. Okay. So basically, I encoded my information with a sequence of Poisson processes with marks, okay? And now what I want to do is explain from this information how I'm going to reconstruct the process for all times. So suppose that you want to, let's take this color. So suppose that you want to compute the height above 0 at time t, okay? So at time t, how tall is the column of blocks sitting on top of 0? So what you can do is you can kind of go backwards in time and say, okay, so I'm going to start at time t, and the height at this time, okay, is just going to be the same as the height the last time a block fell down on top of 0, okay, because the height of the column can only change whenever a block falls down on top of 0. That's the only way in which it can change. So I'm going to start here on top of 0 at time t, and I'm going to go back in time until I see a block trying to fall down on top of 0, okay? And okay, that will be exactly in this case, okay? So here, in that cross over there. So here, I recall that p is equal to 1, so that means that the block will stick to the first point of contact, and the first point of contact will be the highest or the tallest neighboring column, okay? So in order to decide what this block is going to do, at which height it's going to stick to the surface, well, the block needs to see which one of the columns is the tallest one, whether it's this one or that one or that one, okay? So and it's gonna stick to whichever one is tallest, basically, okay? So now what we need to do, let me go back, is to decide what's the height of the columns at this time, okay? So let's call this time t prime or t1. So what I need to do now is I need to compute the height above 0, but at time t1, and I also need to compute the height of 1 above 1 at time t1, and also the height of -1 at time t1, okay? So what I need to do is kind of repeat the same procedure but for now for these 3 columns, okay? So let's say I take this one, okay? And so I continue going backwards in time until I reach a cross, okay? And now I need to compute the time, I need to compute the height at these 3 columns, okay? And okay, so I continue going down, okay? And I determine the height of these columns until, okay, I continue going down until I reach 0, okay? And when I reach time 0, then I have all the information I need in order to somehow determine which one of the columns is the tallest one, okay? And I need to do this for each of these columns, okay? So this one, okay, gave me that one, and this one, okay, will also require me to compute the height at this time for these 3 columns, and then okay, you get the idea. What I will get somehow is a net, okay, of paths which I have to look at, okay, in order to decide the heights of the different columns at the different times. And what these paths do, okay, is that, okay, they start from here. And whenever they reach across, they can either go to the right, to the left, or continue going down. Okay, and okay, so this one will go down until it reaches across, and then it can either jump to the right, to the left, or go down. Okay, and the same for the paths which somehow branch here. Okay, and okay, so this is a kind of a net of paths, and I will need to look at this net of paths to decide what's this height. Okay, and what it turns out, okay, is that, okay, you can disregard this, doesn't really matter, is that the height above 0 at time t for the model with p equals 1, okay, is just the maximum sum of weights. So the maximum sum of the marks that you can collect by any one of these paths on this net of paths. Okay, so you just compute what this net of paths is, and then you look at whichever one kind of collected the most, the maximum sum of weights, and that is exactly our h. Okay, and so with this representation right here, you can see that there's a connection with the last passage percolation problem. This is also last passage percolation problem, which is not on a lattice. It's kind of a Poissonian lattice, because, okay, now the paths somehow need to make jumps whenever you reach a Poisson point. Okay, and okay, that's more or less the relationship between the two models. And so let me discuss, like in 5 minutes or 10, I don't know, a little bit the idea of the proof. Okay, and so let's look a bit at the discrete problem, what's happening with the ballistic deposition model. And so, so as I said before, all these net of paths that I have to look at, I'm going to call them admissible paths. Okay, these admissible paths are the ones that I referred to as a net of paths before. All these guys need to be inside a propagation cone, which is going to be given by the rightmost and leftmost paths, which are admissible. Okay, so what does that mean? That means, let me go back 1 second. That, okay, so any path in this net of paths somehow needs to be contained in the area, okay, generated by the path which every time you see a cross jumps to the right. Jumps to the right. And the path which every time you see a cross jumps to the left. Okay, so in this case, any other admissible path or any path in this net of paths needs to be somehow contained inside this region right here. Okay, and so this region right here will look like a cone. Okay, that's what I was talking about, a cone before. And all the admissible paths will lie inside this cone. Okay. Moreover, these rightmost and leftmost paths, they jump every time you see a cross. Okay, but these crosses actually correspond to points in a Poisson process. Okay, so basically these paths will make a jump every time a Poisson process makes a jump. And so themselves will be, okay, modulo shift or whatever, they will be Poisson processes themselves. Okay, so what will happen is that as t goes to infinity, they will have a slope which is asymptotically the sticking parameter. Okay, and moreover, all admissible paths lying inside this propagation cone right here, again, can only jump whenever they see a Poisson process. They can choose not to, but if they jump, they can only do so when they reach a Poisson point. So they will have a slope which is at most p. Okay, and okay, so that's going to be the kind of the the slope of our paths, and moreover, the number of points that they can collect inside this propagation cone will have a distribution which is going to be a Poisson, okay, Poisson distribution with parameter essentially p to the t squared, okay, and where p to the t squared is basically the area of this propagation cone right here, okay, so that's kind of the number of points they're going to see. And moreover, these points will be uniformly distributed inside this propagation cone, okay? So what we need to do is somehow, for the discrete problem, we need to compute the maximum sum of weights, which can be collected inside a propagation cone, okay, by paths which have slope at most p. And these weights are going to be uniformly distributed according inside the propagation cone, okay. So this looks a lot like the continuous problem somehow, okay. And so what's going to happen is that as t goes to infinity, this propagation cone will actually, the violet one, the purple one, will actually converge in some proper way to the continuous triangle I defined before, okay. And the admissible paths in my discrete system will actually converge once you scale things properly to Lipschitz paths, okay? And moreover, the locations of the weights in the discrete problem will converge to the UNs, okay? Because they are uniformly distributed on this propagation cone. If the cone looks more and more like a triangle, then in the end, these locations will be uniformly distributed in the limit on the triangle, okay? And moreover, if we order the weights in the discrete problem from largest to smallest one, what we see is that if we scaled these weights, okay, the block heights by this parameter right here, okay, where this, okay, I'm telling you what this parameter is, okay, but essentially this right here behaves like pt squared 1 over alpha, which is the scaling from the main theorem, okay. Then you get convergence in distribution to the weights in the continuous problem, in the continuous model, okay. So basically, we see that as t goes to infinity, all the variables somehow of the discrete problem converge suitably to the corresponding ones in the continuous problem. And so the only thing that we need to show is that then the solution of the discrete maximization problem converges to the solution of the continuous maximization problem, okay? Okay, so how do we do that? I will explain briefly. So to obtain the result, what we need to do is, okay, to show convergence of the maximums, okay? So the strategy for this will be the following. We're going to couple both systems, the ballistic deposition model and the continuous problem, okay? The LPP problem, the last passage percolation problem, in such a way that as t goes to infinity, both systems are very close to each other, okay? And to be able to couple successfully both systems, we're gonna need to show that for the maximization problem, only finally many weights matter, okay? That I can somehow disregard all the weights, okay, which are, okay, beyond a finite amount, okay? Okay. Yeah, so basically the maximum sum of weights in this maximum sum of weights in both systems, the main contribution to this maximum sum is going to be given by the largest weights, okay, and the other ones I can completely disregard, okay. And so once I disregard the other weights, I only have I get two systems in which I only have finitely many weights, okay? And once I have two systems in which I only have a finite amount of weights, I can couple them with some work, but okay, I can couple them. And okay, once I can couple them, I can show convergence of the maximums. Okay, and so this is going to be my last slide. I just want to say one word about what or why the alpha in between 0 and 2 is important. Okay, and so the reason why the alpha in between 0 and 2 comes in is that one can show that the optimal path, the path which realizes the maximum, let's say in the continuous model, in the discrete problem, the same thing happens, but it's easier to explain in the continuous model. So what happens is that the nth largest weight collected by this maximizing path is roughly the n squared largest weight of them all. Okay, so the optimal path is going to miss a lot of weights, okay? And essentially the nth largest one it's going to collect is going to be like n squared, the n squared largest, okay? So H, if you think of these heuristics as being true, then H is just going to be the sum, okay, of these weights, because these are the weights collected by the optimal path, okay? But this Mn, these Mn's by definition are just this, okay? And by the law of large numbers, okay, this is just the sum of independent random variables would mean 1. This is just going to be like n squared, okay? To the power of 1 over alpha, okay, that's just going to give you 1 over n to the power 2 over alpha, okay? And this sum is going to converge if and only if alpha is between 0 and 2, okay? And so if this sum converges, what this tells you is that somehow you can disregard the tail of the sum and you can only stick to the first weights, okay? Because that will give you kind of the bulk of the sum, okay? And so once you know that, you can disregard the large weights and you can only work with finitely many, and then you can couple both processes, okay? Okay, I'm gonna stop here, and thanks for listening.
Thank you very much, Santi. Any questions?
So, Santi, hey, so at the beginning you show us some pictures, and there are these like a fern-like things.
This one, or maybe that one.
Yeah, exactly. Yeah, something like that. So this the way in which you prove convergence actually allows you to show that this is the I mean that this picture is more or less what is going on.
Yes. Okay. So, okay, I don't know exactly what you mean by what this picture tells you what's going on, but yes, you can. So the way we show this tells you that the height is only given essentially by the tall blocks. So it's just like the sum of the tall blocks, of the tallest blocks, and the rest is just like dust, basically. And this is, well, I guess one of the things that you can see here, more or less, that like the large part of the height of each of the columns is just given by the tall blocks. So this is something that we can show with the proof.
Okay, and something about the finer details of these tentacle-like structures.
The what? Sorry.
So can you say say something about the finer details of this like a tentacled flowers?
No, we can't say much, because this is this is what starts to look like this, right? Somehow the thing that makes this model easier is that you can restrict to looking at the large weights. That's That's more or less what makes the model tractable somehow. If you start to look at what happens with smaller heights or with shorter blocks, then you get a lot of dependence and correlation, and we can't say anything. We don't know how to say anything.
Okay. So
But do you think it's possible to say anything about the largest height? So as I understood, you were the largest height. I mean, as I understood, we are looking now at the typical height. You fix 0 and then you look at the height at 0. But if you take kind of the maximum of all heights, do you think something like this is possible to say something about it?
Yeah, maybe. So yeah, maybe you can say something, because I mean the model looks a lot like the continuous one. Kind of this graphical representation is very flexible somehow, and maybe you can say something using this graphical representation and this formula right here. But we haven't looked at that. So for example, what we looked at is if you take like correlations, for example, if you take two x's which are kind of microscopically away, then can you compute like the joint limit? And yes, you can. In the end, you get like a joint continuous maximization problem in a union of two triangles or stuff like that. But we didn't look at the max. No.
Okay, thanks. Nice talk.
Thanks.
Okay, any more questions? Okay, if not, thank you very much, Sandy, for a very nice talk. And,
Thank you.
Gracias.
Gracias.
Gracias, Santiago.
Gracias.